So in this session, we study about tautologies. So a tautology is a common proposition which is true under all circumstances, regardless of the truth values of its simple components. So the key thing is that when you draw a truth table for this compound statement, then all the values will be true, regardless of the atomic statements forming up the compound statement. So we'll demonstrate with examples to define tautologies. So the basic example of a tautology is the disjunction of proposition and its negation. So one, the compound statement P or not P is a tautology. Now, to prove this, you simply draw a truth table, and then from that truth table, we show that the compound statement will have all the values to be true. So solution or proof. So I'll have P, and then the negation of P, and then the compound statement, P or not P. So then a proposition P can always either be true or false. And when P is true, its negation will be false. And when P is false, its negation will be true. Now, when P is true, not P is false, then P or not P will be true. The interpretation of the disjunction or, and then when P is false and not P is true, then P or not P will also be true. So therefore, this compound statement is a tautology because all the truth values are true. And then number two, the compound statement given by P implies Q if and only if not P or Q. It's a tautology. So what we do, we draw the truth table and show that this compound statement will all have T as the truth values. So we have this column for P, this column for Q, and then let's have, because we have not P, let's define column for not P. And then we have the implication PQ. So P implies Q. And then we have not P or Q. And then now let's combine P implies Q if and only if not P or Q. So this is the first thing you do. Now, because we have only two variables, so we'll have for rows. So true, true, false, false, and then true, false, and then true, false. Now, when we negate P, when this is true, then negation will be false. When this is true, then negation will be false. When P is false, negation will be true. When P is false, negation will be true. Correct. And then now, let's define P implies Q. So when P is true and Q is true, then P implies Q will also be true. And then when P is true and Q is false, is where we have now problem. So this way we have false. And then when P is false and Q is true, then P implies Q is still true. When P is false and Q is false, P implies Q is just true. And then not P or Q. So we are now relating this column and this is the column. So this is false, this is true. So this or this one will be true. And then false, false, that is now a false value. And then true and true will give true value. True and false will give true value. And then now we want to test the case of P implies Q if and only if not P or Q. So remember the connective if and only if is always true whenever the truth value of the two statements are either all of them true or all of them false. So because this one is true and this one is true, so you expect this one to be true. Because this is false, this is false, they are truth values of the same kind, this will also be true. Because this is true and this is true, then this also true. And because this is true, then this also true. So therefore, indeed, this compound statement is a tautology because the truth value or the truth table, all the truth values are true. So that's how we show that. And then example 3. A compound statement given by P implies Q if and only if P and Q is a tautology. So we do the same way. We draw a truth table and show that all these compound statements will be having truth values of T. So we have column for P, column for Q, and then because we have Q if and only if Q, and also we have and P and Q, so then we'll say P and Q, and then we have Q if and only if P and Q, and then now P implies Q if and only if P and Q. So then this problem has only two variables. So we have for us true, true, false, false. And then we have true, false, true, false. And then P and Q is always true when both P and Q are true, otherwise false. So TT will give T, TF will give F, FT will give F, FF will give F. And then we want now to define Q if and only if P and Q. So remember the connective if and only if is only true when both the truth values of the two statements that are being compared have the same truth value. Either all of them are true or all of them are false. So therefore, TT will be T, FF will be T, but TF will be F, and FF will be T. And then the next thing now, we want to define the implication. So this one now we take it as a unit. This bracket, we take it as a unit with these truth values. And so we compare now the truth values of P and what we have in this column. And remember, implication is always true unless the first statement P is true and then the second statement that is being implied to is false. So when this is true, true, then you expect to have true. True, true will also give true. False, false is true. Remember, this is an implication. And false, true is also true. So therefore, that is tautology, as it should be, because all the truth values in this column, all the values are T. And then example 3, example 4. If we have, so the compound statement P implies P or Q is a tautology. So solution. So just draw the truth table. And if we are able to show that this compound statement will be TT, then it's enough proof. So P, Q, P or Q, and then P implies P or Q. Similarly, we have only two variables, P and Q, so we'll have for rows. So we'll have true, true, false, false, true, false, true, false. And then now P or Q, true, true will be true, true, false will be true, and then false, true will be true, false, false, it's false. Now the implication, P is true and then this is true, so we get true. True, true will also give true. Now false, true for an implication gives true, and false, false for an implication gives also true. Now since all this column has all the values to be T, then indeed that is tautology. And then another example, number 5. If we have not P, so maybe we can put it in a form of a question to check whether it's a tautology. So check whether not P or Q or P and not Q is a tautology. So what we do, we draw a truth table to be able to answer that question, the solution. So first we'll have P and then Q and then not P and then also have not Q and then we have not P or Q and then we have P and not Q and then finally now combination not P or Q or P and not Q. So then now, because there are only two variables P and Q, so we'll have true, true, false, and then false. And then for Q now we alternate true, false, true, false, true, false, true, false. Now when we say negation of P, so when this is true, so we'll have false. This is true, we'll have false. This false, we'll have true. P is false, so negation will be true. Negation of Q, this is true, so we'll have false. False will have true. True will have false, and false will have true. And then let's now combine not P or Q. So we're comparing these two columns, this column and this column here. So false true will give true. False false will give false. True true will give true. And then true false will give true. And then next, let's define P. So this column. So this column P and not Q. So this column here. So and is only true when all the truth values of the two statements are true. So true false is false. And then true and then true is true. And then false and false is false. And then false and true is false. So then now, combining now not P or Q or P and not Q. So simply mean that now we are comparing these two columns. So this column and this column. I remember this connective is OR. OR is true when any of the two values are true. So true false gives true. False true gives true. True false give true. True false give true. So because all the values here are T, then we say not P or Q or P and not Q is a tautology. Tautology because now all the values here are T. So that is how we solve problems on tautology. Simply draw a truth table and show that the compound statement will always be true in all the cases. Thank you.